Swayamprabha. Digital India. Educated India.
Previous lecture talked about some introductory issues on microfluidics. In particular, what is microfluidics and why is it important, what are its various applications, and what are some distinguishing features from the classical classical macro flows. So, this we discussed very briefly. Of course, we will be elaborating on these concepts throughout this particular course, and slowly but steadily we will proceed into the theoretical description of microfluidics. But before that, we will be discussing about certain examples. Now, why we discuss about certain examples is because many times when we are learning a subject, we do not have a big picture, we do not have a motivation. Like for example, like from the first day, if I start deriving Navier-Stokes equation, you will start believing that I mean we are forced to learn the derivation of Navier-Stokes equation or the derivation of some other equations related to microfluidics. I am just giving Navier-Stokes equation as an example, that we will be going through these things with a purpose. So, not just because we have to learn this, and this kind of learning objective is very very important. So, we will try to look into the issue from a somewhat application perspective, that what are interesting applications, what are the outstanding problems that remain to be solved in research, what are the outstanding industrial problems that need to be considered. So, by keeping all these in view, we can go for microfluidic studies for scientific level understanding, for deep technological development, and even for societal issues, and we will talk about these as time progresses. So, that is why I thought that before getting into the mathematical equations and the mathematical details, let us talk about some examples. So, I will talk about some examples maybe possibly in the next couple of lectures, where I will not get deep into the examples, because I will try to get deep into the examples with their mathematical background and all those things for the remaining part of the course. Since we have not yet developed the full theoretical basis of going through these examples, we will better sort of appreciate these examples from from a common man's perception, that right what are the interesting facets that these applications have, and how can microfluidics solve these problems. So, most of these problems are of interesting practical oriented nature. I mean these are not hypothetical abstract problems, these are practical problems. Many of these problems are addressed by my own research group, but I will also talk about a couple of problems which are not touched upon by our own research group, but are addressed by leading researchers worldwide. So, we will start with that. So, some illustrative examples. As I told you that in microfluidics we have broadly two types of applications, bio and non-bio. So, when we say that, it means that biological applications are quite significant and interesting. So, I will talk about one biological example, and I will try to demonstrate that we start with describing a biological problem, but how fluid mechanics is coming into the picture, fluid mechanics over small scales to address this problem. So, this problem is about DNA hybridization. So, what is DNA hybridization? I will try to talk in a very simple terms, and when we talk in simple terms, there is always a danger that you oversimplify the problem. So, please pardon me if I am oversimplifying the problem, this is just for the sake of your own understanding at this level without getting into too much of a depth. So, let us say that well, before getting into the DNA hybridization, let us get into the structure of a DNA. So, a DNA, as you know, has double stranded structure. So, each single strand is associated with a phosphate group, which you see here, phosphate group, which is responsible for the negative charge of the DNA, a sugar and 4 bases, nitrogen containing bases A, T, C and G. So, if you look into the backbone of a DNA strand, then you have alternate sugar and phosphate group, and with each base binded with the sugar that you see in this second panel. So, what it means is that a single stranded DNA is structured like this. Now, how a single strand mates with another single strand to form a double strand? That is possible because A wants to get combined with T and G wants to get combined with C, and this tendency is there because of hydrogen bonding. So, that means that you have a double strand like this, where you see this kind of mating is like A mates with T and G mates with C. So, this is the structure of a double stranded DNA. Now, how can we use this for detection of a disease? How can we use this? So, let us say that like some disease, let us say some arbitrary disease, I do not want to mention any specific disease, has some DNA sequence associated with it. Let us say A, G, T, C, G, G, T, A, C, C, whatever, some kind of sequence, if that is there in the DNA, then we will ascertain that yes, this particular disease is there in the sample. So, to do that, to identify whether that sequence is there or not, we can put a complement of that sequence on the wall of a channel, because if that sequence is there, it will mate with its complementary sequence, and if this mating is successful, then we say that the single stranded DNAs have hybridized to form a double stranded DNA. So, this is what is DNA hybridization. Now, how can microfluidics come into the picture here? See, DNA hybridization typically, so typically what you can do, see, first, see, consider all these processes, like first you have to break the cell and bring the DNA out of it. This process is called as cell lysis. So, you break the cell and bring the DNA out of it. This can be done even mechanically. Okay. So, it can be a pure mechanical process that does it. Then when you break the cell and bring out the DNA, then what you can do, you can heat the DNA, because what you want single stranded DNAs. So, the DNA is double stranded. So, by heating, the double stranded DNA can break into 2 single strands. This is known as DNA melting. This is a very typical name. So, why this is called as DNA melting or DNA denaturation, but melting is also a common term used. Why it is called as DNA melting is because it is like a phase transition process which resembles the melting process, just like melting of ice thermodynamically. So, you can see that there is a biological process which really has nothing to do with melting of ice or melting of a substance, but notionally the thermodynamics may be somewhat related. So, biological processes are also interesting processes involving good amount of physics, chemistry or other fundamental aspects of science. Now, but let us not get into that. So, that single stranded DNA is passed through the channel, and on the wall of the channel you have the sort of the capturing DNA probes. The capturing DNA probes are those which are complementary of what you really want to capture. What you want to capture is the target DNA. So, you can see here that you have a test sample, you have target DNA and these are capturing probes. Target DNA, if that is the sequence that you want to interrogate, then that target DNA will bind with the capturing probes and there will be successful hybridization. But how it will bind? It will slowly move and it will go to the reaction sites. The reaction sites are the walls. So, it is a diffusion process, and as we all know that diffusion alone, if it takes part, is a rather slow process. So, diffusion is a rather slow process, and like it typically, like say the diffusion coefficient of these single stranded DNAs, of course it depends on how many base pairs are there and so on. So, I will not quote any particular number, but let us say it is typically of the order of 10 to the power minus 11 meter square per second. So, it is very slow. So, it will the DNA, the single stranded DNA will take a long time to reach the reaction sites. So, that means that essentially means that for the disease detection a long time will be taken. So, you want to make rapid DNA hybridization. So, to make rapid DNA hybridization, what you want to do? You want to accelerate the movement of the DNA. So, even without applying fluid flow you can do it. How you can do it? Let us say that you apply an electric field. Why electric field is important here? So, this has something to do with the DNA structure. We have already discussed that DNA has a phosphate group. The phosphate group is responsible for the negative charge in the DNA. So, because the phosphate group is responsible for the negative charge in the DNA, if you apply an electric field, the DNA will move because of the electric field. So, this is called as electrophoresis. So, if you have a charged particle, see the DNA is not a particle. So, see we will study later on electrophoresis in this particular microfluidics course. So, I am just giving you a motivation that why study electrophoresis out of so many things. See, it will give you we will study electrophoresis of a sphere in a flow field. So, when we study electrophoresis of a sphere, see DNA is not a sphere, but many times DNA is modeled with an equivalent radius of gyration. So, you see that this is what is mathematical modeling all about. There is a physical reality, you cannot represent the entire physical reality by a mathematical description because the physical reality is very complex. So, what you try to do? You try to simplify the problem and represent the essential physics in terms of some mathematical equations, boundary conditions and so on. That is what is mathematical modeling and simulation all about. So, we are not in most of the cases representing the actual problem, that is why we call modeling. See, it is not the actual problem, it is a idealized representation of the physical reality, and when we do that we have to keep in mind that the actual geometry and all those things may not be well captured. So, we can apply an electric field and the DNA will move, but there are several issues associated with the use of electric field which may not be so advantageous. So, it might accelerate the DNA movement, but there may be several other features which are not so favorable. I will not elaborate on those features now, because we will discuss about these in more details as we progress in the course, and as we discuss about biomicrofluidics we will talk about those things, that what are the positive and negative consequences of applying electric field on a DNA sample, we will talk about that. So, but here we try to see that well electric field being not being always the most favorable solution, let us consider some alternative mechanical means, pure mechanical means of accelerating the DNA transport. So, this is a research problem on which we worked in a collaborative project with Professor Mark Madu's group in the University of California at Irvine, and I mean it was funded by one Indo-US research program, and what we proposed and was something like this. So, I will just run a movie which will which is showing that there is a flap which is oscillating on the wall of a microfluidic channel. This is a flap not made of a rigid material, but made of a flexible material called as polypurol. So, this flap is flexible, and what it is doing is, when it is oscillating, it is oscillated by an actuator, the actuator may be electrical actuator. So, when it is oscillated by an actuator, the fluid which contains the DNA sample is being, you see that because of its oscillation it is being targeted towards the wall. So, this oscillator is acting simultaneously like a mixer and a pump. So, it is sort of directing the flow in a certain direction. Now, when it is doing that, is it satisfying the entire purpose? You see that if you look at this view graph, you will see that there may be various DNA test sites, not just one single DNA test site, because you may be interrogating several diseases with one particular sample. So, there may be several target sites. So, if all the DNA falls on one site, then the next site will not get the DNA sample from the solution. So, you want to make sure that all the sites get the requisite amount of DNA from the sample. So, how do you do that? To do that, what you do is, instead of using a single flap, you use multiple oscillatory flaps. And the design problem, see, you see, when you use multiple oscillatory flaps, then all the DNA does not fall here. I mean the DNA, I mean here in this example just 2 flaps are shown, but it could be n number of flaps, and it is very important as a design problem, and this is the pure CFD problem. It is important as a design problem that what is the amplitude of oscillation, what is the frequency of oscillation, and see, in terms of a CFD problem, it is not a very straightforward CFD problem. These kinds of problems in CFD are called as fluid structure interaction problems. So, there is a structure which is an oscillatory structure, the fluid is interacting with it, but the structure is a flexible structure, the structure is not a rigid structure. So, the flexibility of the structure plays its own role, that alters the pressure in the surrounding fluid, that pressure alters the flow field, and that flow field in turn dictates the oscillation, I mean in turn influences some of the oscillatory characteristics of the flap, although it is in addition externally controlled. So, there may be a two-way coupling between the flow and the structural motion, and this kind of problem has to be approached by considering the mechanics of solids and mechanics of fluids over small scales. So, what I want to impress upon you is that to design this kind of setup, see, we started with, when I first started narrating this problem, many of you might have been frustrated because we started with phosphate groups, sugar, base, all these things. I do not think that many of you have come to engineering to study phosphate group or sugar or base or these kinds of things. But when we went into the final solution of the problem, you see we are talking about the fluid flow equation, the structural mechanics equations, the CFD and all those things, and many of you I believe are interested in these areas. So, you see this is what is a modern outlook of engineering, that right, you can use engineering skills not just to solve traditional engineering problems, but some problems of these kinds, and this is one of the very important applications of microfluidics. Let us get into a second example. Let us again prepare a little bit of background of this example before we get into this example. In many scenarios, even in classical fluid mechanics, we are bothered about that how to drive a flow. Like as engineers, we are very much bothered about how to drive a flow through a system. So, when we say that how to drive a flow through a system, we essentially mean that, right, what is the mechanism by which we drive the flow. For example, in the large scale system, we require pumps to drive a flow, and of course, what is the penalty that we have to pay to get a particular output. That means, say, what is the pressure drop that takes place for a particular flow rate, something like this. These are very common facets which we tend to address when we are designing a transport system. Not just a classical system, even in a microfluidic system these are important, just that we may not use classical pumps, we may use pumps I mean which are like typically say syringe pump, peristaltic pump. We will talk about these pumps and we will show you demonstration examples of these devices. So, these are I mean these are not pumps in the very classical sense, but these are like pumping devices which can actuate fluid flow. But now many of these devices have their own shortcomings, like for example, these devices have mechanical components, and mechanical interaction like say frictional interaction for example, these are associated with losses, and in a small scale system these losses are very significant. Like if you recall, I mean we will again get into all these because I can understand that there may be some students here who may not have a comprehensive background in fluid mechanics, but just to reiterate that at least if you have if you recall the fully developed laminar flow through circular pipes for example. So, the head loss is given by the Hagen-Poiseuille's equation. So, head loss is inversely proportional to the fourth power of the hydraulic diameter. So, that means if you reduce the hydraulic diameter from 1 meter to 1 micron, you see by how many times the head loss increases. So, with that very significant head loss and with also like mechanically moving components working unfavorably over small scales, you need to look for alternative strategies of driving the flow, and that is where like a big a whole lot of activities are going on in the area of alternative flow driving mechanisms in microfluidics, like flow driving by electrical field for example, and we will discuss in length in great details about how to drive a flow by electric field and the entire science and technology behind that. It is a big part of this particular course, but we have to understand that the electrical field also has its own limitations. So, can we go for alternative techniques? So, I will show you one example where we can move water by light, by optics. So, how it is possible? So, let us consider an example. Let us look into this T-shaped microfluidic channel. So, T-shaped micro channels are very commonly used for droplet generation, because if you are passing some fluid, then at the junction because of shear the continuous fluid may get broken into droplets. This is one of the mechanisms of droplet generation, but here in this particular example we will not focus on droplet generation, but something else. So, let us say that we are injecting the fluid, say deionized water from this bottom of the channel. Now, it enters the junction. Now, we have to decide that whether we want to transmit the fluid towards the right or towards the left. So, this is